what is a cosmic ray flux? The Earth is receiving enormous number of cosmic ray, high energy particles every time. It's coming through our atmosphere and forms some sort of cascade and other patterns that my friend will discuss a little bit later. So our question is, does sun affect the cosmic ray? Okay. Sure, Moitra. So our question is, does it affect the cosmic ray flux? If so, then how much? To what extent? So we followed basically two paths, two major events that happens in sun to answer this question. The first one is solar eclipse, and the second one is solar flares. Yes, something more is awaiting there, so we will come to that later. Now, before going into further details, I would like to ask, I would like to request my friend Priyajit to continue a little bit about study of muon flux on Earth.
Uh, Thank you, Aiko, for your nice explanation. So let us move ahead. The cosmic rays are full of high energetic proton, and like the nuclei of hydrogen atom and any other excited molecules. Like after entering into the Earth's atmosphere, it collides with the nuclei present in the atmosphere, and in this collision, like many particles like baryons and muons, for example pions, kaons created, and we call this particle as a primary cosmic ray. So but and we know that baryons and pions are not that much stable, so they immediately decay into like secondary cosmic ray particles like muons and muons, antineutrino. So and you can see the decay equation below from the now the above process, the process given in the slide is called the cosmic ray air showers. So in this process a huge amount of muons is created, and this muon start to fall towards the earth, and muon has a lifetime of like 2.7 microsecond, and after that is decay into the electron and pair of neutrinos. So now let us discuss how do we detect the muon. So we generally use a scintillator to detect the muon. Scintillator basically is like made of some luminescence material like sodium iodide crystal or like that. So when a high energetic muon passes through a scintillator, is deaccelerated and radiates energy. So the free electron in scintillator got excited and goes to a higher energy state, and when it comes down to the ground state, it releases energy as a form of light. So and we call this process as a luminescence. So and this and the photon then hit the photodiode and produces the number of electrons, photoelectrons, through photoelectric effect, and after that the number of electrons amplified through a dynode chain by the process of electron multiplication, and the electron pulse is generated. And if the electron, I mean, we set a threshold energy, because there besides the muon there are also background radiation, but the energy of the background radiation is very low, so we set a threshold energy. If the energy of the pulse is greater than threshold, then it will trigger the discriminator, and the counter module will count the event, otherwise it will not count the event. So at last the computer will execute the output signal as a histogram of signals using MCA. So our first study is based on like solar eclipse. So why do we choose solar eclipse? Because we know that in solar eclipse, between earth and sun, the moons come. So a huge mass comes between sun and earth. So it's so we should expect a dip in the muon flux. So for this study, we have considered the major solar eclipse that happened on 21st August 2017, which mostly affected a vast portion of the USA and Canada and Mexico. So we have taken various detectors across the USA and studied the variation in flux, and also tried to explain the possible reason behind our observation. So here is our result we calculate from the data. So basically you can see the variation is not that much, it's between 1 to 2%, except the Syracuse University, there we got a variation of 4.72%. So we tried to find out the possible reason behind them. So let us discuss that. So like in all or in almost all detector we are getting a variation of muon flux like 1.2%, but in Syracuse University we are getting a little bit higher. So the possible reason could be like the instrumentation error in detector or the weather condition of that day, because like temperature or pressure can affect the muon flux, or maybe the cloud and humidity. So let us say like we have calculated like a performance study of the detector, and it comes like a Gaussian distribution. So the detector was working perfectly. So the second reason was like the weather of the day. So the day we found that like there was a cloudy weather and the humidity also was high. So this could be the possible reason behind the deep in the muon reflux. So here is our second study. We will discuss.
So before going to the second study, I would like to make a few comments about the first thing. So while we are detecting about the, I mean, whether there is some variation or dip during the solar eclipse, we found a very nice pattern among the data. I mean, mostly in all solar eclipse, we studied one mostly, but mostly it is not that much. And the variation of the variation during this time, the solar eclipse time, it is not out of the normal range of variation. Usually there are very much no, I mean, there are many things, many other events happening in the universe. So mostly it's within the regular range of variation. But Syracuse showed a very strange type of data. And my dear friend Priyajit explained that there may be two reasons. So the performance, we can expect it Gaussian because it's I mean n tends to infinity number of data for for a binary process, like, so we can expect that to be a Gaussian pattern. But here we have seen that the pattern of Syracuse University detection procedure is nicely Gaussian, and it fitted to the Gaussian distribution very nicely. The parameters were very nice, but weather was a big issue here, and we can see that at the time of eclipse there is a partial on the cloud was there which covered the sun, so humidity is also affect. But there are some confusion about humidity, and the work is still going on about humidity, how it is varying, how much, how is the effect of humidity. And Earth's weather is a very strange, I mean, it shows a very strange behavior. It actually, there are many issues going on, and we are also not clear about that. And I think there are places that where we can need study later. So I will say about it later also. Now let us go to the second part of the study, the variation of muon flux during solar flares. So before going into that, I will start from a little bit basic stage. First, starting from a basic story, a very small story. The day sun brought darkness. It was a very spring morning, 13th of March, 1989. But in Canada, Quebec, the people in Quebec almost they faced a very severe condition as the electricity was down for 8 to 9 hours, as quote unquote some coronal mass ejection happened, according to the scientist. So we'll study what is that and why does it affect the muon flux, I mean the earth life, or does it affect the muon flux? So we'll study that. Also, there was another thing. 4 days prior to this event, on 9th of March, solar astronomers found a very strange pattern on the surface of sun as some sudden explosion on the surface happened. Now the question is, can some sudden explosion on the surface of sun put a drastic effect on Earth? So can we guess this with our muon data? Let us find out. So first, going into the details, we need to know what is solar flare, or what is this gigantic explosion that happened on the sun's surface. Solar flare is intense electromagnetic radiation and sudden explosion of energy in the sun's atmosphere due to reconnection of magnetic field. I will come to that later, but this is due to some reconnection of magnetic field. Flares occurs from active region of sun which are associated with the sunspot. Basically, we know the sunspot has two sort of ends, and due to the magnetic reconnection, the magnetic energy converts into kinetic energy, and charged particles are extremely accelerated. The charged particles comes as a burst. So now solar flares occurs when these charged particles interact with the plasma medium. During the solar flares, solar particles event happens, and which we want to study from our muon flux data. And sun releases a huge amount of charged particle, mostly protons. Now, when sun is ejecting some sort of high energy particles or mostly charged particles, we can expect some of it can come to the Earth's atmosphere and form the natural cosmic ray cascade as we expect. And we can expect a little bit variation in the muon flux data. So does it affect? Before going, here is two pictures. It's a picture of magnetic reconnection. I will come to it later also. And this is the event of solar flare that is happening on sun surface. We can see the nice pattern of solar flares. It's a very nice event to look even. So this is the coronal magnetic loop of sun surface. The image was, it was taken from Nature's Third Cycle by Professor Arnob Rayachowdhury. And now coming to talking about sun, I must say sun has two types of magnetic field. One is poloidal, one is toroidal. Now the poloidal magnetic field, to tell this, I need another theorem. This is Auswen theorem of flux freezing. We know about the Kelvin-Helmholtz theorem for fluid is very famous theorem, which states that the flux, integration over the surface, over any surface S or surface area S of the vorticity with an element ds is constant over time. So basically, for the magnetic version of Kelvin-Helmholtz theorem is Auswen theorem of flux freezing. In Kelvin-Helmholtz theorem, the vorticity, the vortex tubes are sort of carried by this thing, the flow. And here, for the Auswen theorem, when we are considering the magnetic field, if the electrical conductivity is very high or the resistivity is very low, tending to zero, which happens for plasma, because in plasma we know that the electrons in the nuclei are sort of separated, and that's why it has an enormous amount of electrical conductivity. Also, there are issues in plasma. It's a book. It's a book by Professor Arnob Rayachowdhury, and it's a famous book. So for this, we're talking about is plasma. So in plasma, we know even in plasma, the electrons and the other positively charged portion is separated, and which allows it to be a very good conductor of electricity. And as the conductivity is very high, that's why it is a good, it follows the Auswen theory of flux freezing very well. And as the flux freezing happen, we know there is a poloidal magnetic field in sun, but in sun, there is also a nice event always happening, that with the along this axis, along the z axis, if we consider this axis to be z axis, then along this axis, the velocity is variable. It has differential rotation rate. Due to the differential rotation in the sun, the magnetic flux, the poloidal field will just distort in some, as a center part, center part or the middle part of the sun has greater velocity, this portion will tend to bend, and this bending increases like this like the diagram as is shown here in the Auswen theorem of flux freezing. And as it happens, this vertical field generates to some horizontal small scale fields, and this leads to the toroidal magnetic field. That's how the poloidal magnetic fields generates the toroidal magnetic fields. And as the toroidal magnetic fields, as a poloidal magnetic field generates the toroidal magnetic fields, now a strange thing happens in sun, that this magnetic flux tubes in the sun's convection zone rises above. It happens because of one issue. Because inside the flux tube, we have a greater density of the magnetic field lines. It leads to a magnetic pressure outside. The magnetic pressure is just the gradient of B square and over some constant. So basically, it allows the internal pressure of the flux tube to be less. I mean, pressure due to the gas or the plasma to be less than the outside. That means it has a less density than the outside. As the density is less, according to the Archimedean principle, it goes above, and after a certain extent, it crosses the surface of sun and forms this active region on sun's surface, namely the sunspots. In this sunspot, we used to observe the solar flares. Now, how this solar flares happens, and how in this sunspot the solar flares happens, I previously said it happens due to magnetic reconnection. Magnetic reconnection we can qualitatively describe by this diagram. Here, there are many flux rings within this surface, mainly the coronal part. There are many flux rings. If we achieve some sort of this sort of configuration, like one is going this way and one is going this way, in between, in the middle region, there's a vertical electric field. I mean, the vertical current in this region, because we are having this way a magnetic field and this way a magnetic field. This will leads to some current in this region. Now, in this region, the resistivity will come in action, and as we know, and as the resistivity will come, the temperature will the current will dissipate current will lead to some power. It will form some power, and the region will be heated. And as the region is heated, it is again becoming less density, and regions from the fluid from this region, the plasma from this region is coming to this point. And as they are coming, the magnetic field lines are also coming. And after a certain extent, these two oppositely going lines will merge and form this sort of line. So it will just, these two will form, and this will annihilate, and this will join. In this process, the magnetic field in this region, due to the resistivity, decreases with time. And this leads to the energy, this leads to some energy ejection, which changes in the form kinetic energy, and which forms the solar flares event. Now, as during the solar flares, the particles are accelerated by this energy, and they comes as high energetic particles. But there is a strange thing here. I will come about it later, which is known as Parker helix. I will come to that later, because this is some drawbacks which we faced during our experiment. So before that, I will go to the part of the experiment that we are focused to do. So as we have discussed, during the solar flares, high energetic particles comes out, and this leads to, we can expect some of these high energetic particles should come to Earth's atmosphere, form the cascade as my friend Priyajit described, and we can see some variation or some increase in flux during this cosmic ray flux or muon flux during this time. We have taken data from 1st September to 10th October. In between, there was a very nice solar flare event. So that time we have taken, and we have seen Concordia, Fermilab, Pune, where our detectors, where the coordinate detector is situated. Every time there is an increase in flux during this period. We can also see in the data there are other variations. Every time there are some variation, but we have taken taken across various latitude and longitude, so that we can guess about the pattern, like whether this increase is persistent or not in every pattern, or whether there is some local noise on something other thing is there in those regions. So every time we have found there is an increase in flux, and this is persistent over various flares also. On between 16th of October and 16th of November 2021, again data was taken, and again there is flux rise during this solar flare event. And also the flux rise is used to be this is the date when the solar flare happened, and after that there is a peak, and then it is decreased again. It happens within 3 to 4 days, the peak remains. So it's a general pattern followed in every solar flare, and we can expect this 4 days, because the 4 days comes from, because we know that the high energetic particles will also need some time. The solar wind will also need some time to come into this, pass this region. So this is the overall pattern. Now there is one more question. that Earth is also have some magnetic field. Now, does it affect the detection of muon flux, or does it affect this increase in muon flux? Usually, the because the latitude and the altitudes is different at different detectors. So usually we can expect that even during every time, even during every from everyday data, we cannot detect that how the muon flux, how the muon rates are there when we are measuring it in from Earth's perspective. Like we know that the Earth's magnetic field is sort of perpendicular to the, it's sort of along the zenith in the polar pole regions, and it's so in polar regions, the charged particles should come in helical pattern. So in polar region, the chances of detection of muon is greater. So does it affect? We cannot study from regular data. We have taken this flare data to know whether whether the muon flux is varying according to the theory, like according to the magnetic field of Earth, that as long as the magnetic field is changing its declination and inclination angle, whether this thing is showing variation. And for that, we have taken majorly two data set on 28th of October and 10th of September. For this, we have taken only the horizontal component of Earth's magnetic field. This is because the horizontal magnetic field is along horizontal direction, and the particles are coming from vertical direction. So as we know, the magnetic field will change the direction of the charged particles as q v cross b. So v cross b, v and b should be perpendicular for that, and we have compared the percentage rise during this during the solar flare with the horizontal component of Earth's magnetic field. And for 28th October and 10th September, we have seen a clear pattern that as the horizontal component is decreasing, the percentage rise is more. That means that if the horizontal component is less, the percentage rise, the percentage, during the flares, the increase in flux is constant. Increasing flux, say for example, there is a certain increase in flux, but as the horizontal component is varying, this percentage is varying over over the horizontal component, because some particles are shielded due to the horizontal component and is deflected outward due to the Earth's magnetic field. And clearly we have seen there is a clear negative correlation with the horizontal component of Earth's magnetic field. The correlation coefficient for the 28th of October data came to be minus 0.89983, and for the other thing it came like 0.97207. So we have seen a clear pattern in that. Now the theoretical justification I just said, like this is the part, this is the way the particles are coming, and this is the horizontal component. This will be a deflection force. So the cosmic particles are coming at very high speed, and electron charge is there. So horizontal, because the muon charge is also like that. So the horizontal component of Earth's magnetic field, if it is B, then it will deflect by this region. So what will happen at polar region? The deflection force will increase as the magnitude of Earth's magnetic field increases. Due to this, the solar storm does not affect much in the other region. But in polar region, the pattern of this is quite unusual, as the magnetic dip is 90 degree, and the particle shows a helical pattern there. But there is one major drawback here, that the coordinate community doesn't have any detector around the polar region. So it was hard to detect in the polar region that whether there is an increase in this region. We have taken data for a quite good amount of latitudes and extrapolated that to the polar region, like this will be the increase. Now this is the challenge. So we haven't studied how the others magnetic field, others two component of Earth's magnetic field changes this, the declination and the dip, how they are like, how they affect the Earth's magnetic field, and how much different it is in the poles, like I have said again, and how it changes during the 11-year cycle of sun. We know that the sunspot cycle, the cycle of sun is 11 years, and during the maxima of the solar, maxima, there is a high, the solar flares are quite frequent in this region. So we haven't studied for that. The major problem, because the coordinate community is not that old, and the data in the old sites doesn't have that good performance. So that's also a challenge here. And I have also mentioned one thing while studying, while saying about the previous things, like the Parker helix. To say about the Parker helix, I must say, when the solar particles event, the high energy particles comes out of the out of the sun's corona, that the coronal mass ejection happens, it doesn't the pattern of the cosmic rays or the solar storm is not very uniform. It comes as a Parker helix, that's some helical pattern out of it. And if earth is within if earth is within this region, this path, then only we can verify the effect of such solar flare. So to see the prominent effect of a solar flare, we should expect to study about some we should expect to study when the solar flares is affecting the earth, but it is not happening every time. And that's why the rise in flux, we have seen earlier that, I'm going to the earlier data ones. We have seen there are very regular variation, but in 1989 we don't have the muon flux detector as we have now. So I must say, if we study the data during some high some if, some time when the muon when the solar particle event affected the earth very much, then we can expect that the variation would be much higher. But as it is not that frequent, and as it is not in our hand, we need to wait for some time and need to see whether this thing actually increases or how much increase is there, and how in different layers how the increase is there. We can qualitatively study the energy that is ejected in these flares also, how this happens during this time. So these are these are few aspects which I and Priyajit both think that in future these things can be, we can consider this thing. So these few things are there. Now I will ask Priyajit to make the concluding remarks about our work.
So like from our two experiment, we concluded that the variation of muon flux varies not that much, and the contribution of sun in our in muon flux that is coming to earth, it's not that much. It's between like 5 to 6%.
Yes, from this
From this
eclipse data
eclipse
and
data. So these are the possible these are the resources we used for our experiment. And if anyone wants to if anyone interested about muons or want to do some experiment, you can visit QuarkNet website. They regularly upload the data there. So thank you everyone for your time and patience, and if you have any question, please ask.
it's a community about all over the world, and in India we have two sites for this thing, like Ayuka and Miranda House, which are the collaborator of this huge circle. It's a community which works on muon data and which has two types of detection procedure. One is about the scintillator detector and one is CMS detector. So this is a community, and we were there in Miranda for the last summer in 2021, and during that time we collaborated in this. Yeah,
Yes,
we were
yes.
that time the pandemic was there. Yes. No, this is not random. I will go to my slide once more. So basically, on 28th of October 2021 and 10th of September 2017, there are two major solar particle event. That is the solar flare event. So we have studied the data corresponding to it. A 1 month variation along the date, plus minus 15 days. Yeah, thank you much
Thank
also for this opportunity.